Hey folks, this is our final lesson in our reaction rates and equilibrium unit. And what we're going to be talking about is something called the equilibrium constant, which is represented by a K, as so many constants are, with a little subscript EQ afterwards to indicate, equilibrium. So this is where we're finally going to do a little bit more numerical stuff to kind of put numbers to the concepts that we've been talking about throughout this unit. So 3 big goals for this lesson. First, we're going to talk about what an equilibrium constant actually means. So when we get this number, KEQ, what does that actually tell us about the reaction? So that's our first goal. Second goal is to figure out how to basically calculate an equilibrium constant for a given reaction. And then our last goal is to practice solving some problems that involve the equilibrium constant and concentration of various reactants and products in our system. Okay. So first goal, what does an equilibrium constant actually tell us? Basically what it does is it gives us an indication, some sort of numerical value to which direction our reaction prefers to go in. Now, as we've been talking about, reactions can go both ways. They can go forwards, that we're using up our reactants to create the products, or they can go in reverse, basically, where instead we're using up our products to create more reactants. And as I mentioned before, those two values are not always equal to each other. We don't always have equal amounts of reactant and product. By looking at this equilibrium constant value for a reaction, we can start to guess whether we're going to have more reactants or more products for a given reaction. And basically we calculate this equilibrium constant using the concentrations of all of our various substances in our system. Okay. So the first option is that our equilibrium constant can be a really big number. So if we thought about it in scientific notation, which we will frequently be using, it's going to be some number times 10 to the big exponent, times 10 to the 8th, times 10 to the 10th, something like that. That's going to tell us that we have a really big number on our hands. And what that means then is that our reaction tends to go forward. So we're using up our reactants to create products. Products are the things that are being favored in this reaction. So an example would be this reaction shown right here, where we've got silver and chloride ions coming together to form silver chloride, the solid. Now if we see the equilibrium constant for this reaction is 1 times 10 to the 10th. That's a really big number right there. I can tell that because of that big positive exponent on the 10 in scientific notation. So that means that in this system here, where we've got some silver ions, some chloride ions, and some silver chloride, we're going to have a ton of silver chloride, the product, and not a whole lot of the silver and chloride ions, the reactants. For the most part, most of these atoms tend to prefer to exist as the product rather than as the reactants. The other option then is for our equilibrium constant to be a very itty-bitty number, much less than 1. And as you might expect, what that means is that this reaction would then favor the reactants, that most of what we have as reactants, we don't have a lot of product forming from that reaction. So an example is right here. Okay, we see our equilibrium constant has an exponent on the 10 that's a negative number. Okay, the fact that it's a negative number tells us that what we have is a very small number, 0.000018. That's a lot less than 1, which means that in this situation we're going to get a lot of this CH3COOH and very little of the ions that form it. For the most part, we're going to have our reactants and very little of our products. Okay, so that's the physical meaning of an equilibrium constant. It just tells us whether we're going to find more reactants or more products. Okay. Now, if we want to calculate the equilibrium constant for a given reaction, what we have to do is look at the substances in that reaction and look at the coefficients out in front of each substance in the balanced reaction. Okay, now what we have here in this red box is sort of a generic form, which I know may look kind of scary, but just to break this down a little bit, we're building this based on this balanced reaction shown to the right. So in this situation, our reactants are substances A and B, whatever they may be, and our products are substances C and D. Okay, so what you notice is that my equilibrium constant is just a big fraction. And on top of the fraction, I have the concentration of each of my products raised to the power of whatever the coefficient out front is. Okay, so for example, substance big C has a coefficient of little c. So to start my equilibrium constant, I would take the concentration of whatever substance big C is, and then take that number and raise it to the power of little c. Okay. Then I would multiply that by my next product, which in this case is big D. So I take the concentration of capital D raised to the power of the coefficient on that substance. Okay, so I do that for all of my products, and then I divide that by the same thing for all of my reactants. So the concentration of my first substance raised to the power of whatever the coefficient is, times the concentration of my next substance raised to its coefficient, blah, 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 blah. Okay, one thing to note for this is that we're only going to use substances that are either gas or aqueous in this thing. If you come across any reactants or products that are either solid or liquid, you just skip over them and pretend they're not even there, which is pretty nice. All right. Now I realize this is all very weird, abstract, theoretical, so let's look at it with an actual reaction. So I've got this one right here where we've got nitrogen gas. 1 mole of it reacts with 3 moles of chlorine gas, and that's in equilibrium with 2 moles of nitrogen trichloride. Right? So to write the equilibrium expression, okay, what I do is on top I start with the concentration of any products that I have. In this case I only have one product. It's this NCl3. So whatever my concentration or molarity of NCl3 is, I'm going to raise it to the power of 2 because that's the coefficient I have out front, which is why I've got the concentration of NCl3 raised to the power of 2 in my numerator. Now in the denominator I do the same thing but with my reactant. So my first substance is N2. There's no coefficient on that, so it has an exponent of 1. And then my next reactant is Cl2 with a coefficient of 3, so I'll take the concentration of Cl2 and raise it to the power of 3. Now I included all of these because they're all gases. If any of them had been a solid or a liquid, I would have just slashed them out, not even counted them. All right. Now, that's just an expression to describe the equilibrium constant. That means we can actually calculate a number if we know the concentration of each of our substances. So let's say we go into our system and we figure out the molarity of each substance in our system. We've got this molarity for our N2, this molarity for our Cl2, and this molarity for our NCl3. Okay. Once I've written the equilibrium constant expression, all I have to do is plug in my numbers at that point. So here's that same expression that we did previously using that balanced equation for our reaction. And now I'm just going to plug in the numbers given to me. Each of those different concentrations just goes right in there. Okay, so for NCl3, I put that in. For N2, blah, blah, blah. For Cl2, blah, blah, blah. Just plug and chug. All right. Now my recommendation to you, since this can get kind of hairy with lots of exponents and whatnot, is just to focus on each substance separately. So just find out what 1.41 times 10 to the negative 1 raised to the second power is, and do the same thing for this guy in the sort of salmon-y color, and again for the stuff in green. Okay. So once you've done that, you've greatly simplified it down, and then you can continue to just plug that sucker on into your calculator from there, remembering to put parentheses around your entire denominator. And what we get is an equilibrium constant of 2.35 times 10 to the 13th power. Now hopefully what you notice, this is a very large positive exponent. So what that means then is, since we have a big KEQ value, this is a reaction that favors the products. We're going to find way more NCl3 than we'll find N2 or Cl2. Okay, way more product than reactant. All right. Now lastly, we go and mess with our system, because that's what we like to do in this unit, is mess with these poor little molecules. And we let some chlorine gas out. Okay, so then our poor system scrambles, it shifts over to the left to try to make up for some of the chlorine gas that's been lost, and eventually we re-establish equilibrium. The system kind of balances out again, forward and reverse rates are evening out, and we're good. Everything is fine again. All right. Now, when this happens, we now have new concentrations of our different products and reactants, because, you know, we lost some stuff. So we find our new concentration of our chlorine gas and of our nitrogen gas. From that, we want to figure out what the concentration of our NCl3 must be. Okay. Now here's the cool thing about an equilibrium constant. It stays the same. Okay, so now that I've already calculated that my equilibrium constant for this reaction is 2.35 times 10 to the 13th power, it's always going to be that. All right, so even though I went in and messed with my system a little bit, I can still use the same KEQ value even though my concentrations have changed. All right, so what that means is I can just set that value equal to that same equilibrium constant expression that I wrote before. Okay, so just again to kind of take us back. All right, we wrote that our equilibrium constant was equal to this expression. Now that I have solved for that KEQ value, I can just set that equal to that same expression from before. Okay. And in this situation, I also can plug in the values for the concentration of N2 and Cl2, which leaves me with just the concentration of NCl3 to try to figure out. Okay. Now I've run out of space, so here it is again, same deal. Right. If I go and multiply everything in the denominator together, I get this number. And then I'm going to multiply this denominator by both sides to get NCl3 squared by itself. And then just to get the concentration on its own, I'll just square root both sides. And I determine that the new concentration of my NCl3 is 9.79 times 10 to the negative 6 molar. Okay. So again, what's nice about the equilibrium constant is that it's always the same for a given reaction. Once I've solved it, it's done. So even if I go messing with the concentrations and adding stuff and taking stuff away, it's still always going to be the same KEQ value for a particular reaction, which is kind of nice. All right. Now we're going to go through one more example just to kind of solidify this stuff in our minds. Okay. So here's another reaction that we've got here. Whew. Yikes. All right. So if we want to write the equilibrium expression for this reaction, again, we go with the products in the numerator and the reactants in the denominator. And we get this. Now what you might notice is, wait a minute, we've got two products, but only one thing in the numerator. That's because one of our products is a liquid, and we don't count liquids in the equilibrium constant expression. So as soon as we saw the liquid, we just said, I don't care. We only worried about the things that were aqueous or gas, okay, which is why we've just got one substance on top, two substances in the bottom, each one being raised to the power of whatever its exponent is. Right? Now, for this particular reaction, if we were to go through and calculate using, actual concentration data, what we would find is an equilibrium constant value of 1.95 times 10 to the negative 4th power. What this means, okay, again, to figure out what it means, we have to figure out if it's a big number or a small number. To do that, we look to the exponent on the 10. We see that it's a negative number. That tells us that this is a small number. The fact that it's a small number tells us that our reaction tends to prefer reactants rather than products. What we're going to find is more of these things over here on the left and less of the things over here on the right. Overall, we prefer the substances on the reactant side. All right. Now, let's imagine that our system ends up getting some extra chloride ions. Maybe there was some silver chloride in there and those dissociated and released extra chloride ions. Okay, so we get extra chloride. That's a stress on our system, so our equilibrium position shifts to offset that stress. And we end up with a new equilibrium position with new concentrations, and we want to find the new concentration of one of our reactants. Okay. Now to do that, again, we're just going to plug everything in. We know the value of the equilibrium constant, so we can set that equal to that whole mess that we came up with on the previous slide. All right. And then plug in all the concentrations that we know, so that ultimately we're going to be able to just solve for the one missing concentration. Okay. Now to solve for this, again, I've got something that I don't know in the denominator. I hate that, so I'm going to cross multiply, bring it all over here, and then divide both sides by this whole thing in green, which I got by multiplying this number times this number, the 1.95 number, times the 6.7 number. Okay. Then divide by that to get the final concentration of my reactant. Okay. That's all I've got for you. We'll do some more practice in class. Have a fantastic day.